Okay, so hi to everyone. It's a great pleasure to be here, and I'm very excited. So I'm going to talk to you about how I hacked Minesweeper, and I'm going to use this talk as an opportunity to show you some concepts in reverse engineering. First of all, let me introduce myself. So my name is Ophir Harpaz. I'm based in Tel Aviv, in Israel, and I work as a cybercrime researcher in a company named Trustir, which was acquired by IBM Security a couple of years ago. What I do during my work hours is I read a lot of JavaScript malicious code that aims at attacking banking applications online and basically stealing money. But when I come back home from work and when my boss is not there, what I really like doing is reading assembly code and analyzing Windows applications and reverse engineering. I just created an online workshop for reverse engineering. It's called begin.re, and it's for extreme beginners like I was a couple of months ago. And you're very welcome to visit it and try it yourself, and I would love feedback if you want to give it. So the story of Minesweeper and me begins about a year ago when I worked in Checkpoint Software Technologies in Israel. And in Checkpoint, I met a very talented researcher named Aviad Carmel. And he gave me Minesweeper as an exercise to improve my reverse engineering skills. And what made me so excited about it was that Minesweeper was the first real-life executable that I actually handled. So before that, it was just crack me's and like exercises, and this was the real thing. So this is why I liked it so much. So the goals of this talk, it's a 30-minute talk, and the three goals are first to just show you a nice trick on a game that we probably all know, and show you what can be done using reverse engineering. The second thing is to use this as an opportunity to show you how the architecture works, how the x86 architecture works. And the third is maybe to encourage you to grab an executable yourself and try to change it according to whatever you wish. This is very cool, so I hope you'll enjoy it. Before we dig into Minesweeper, there are a couple of things that I'd like to overview and to give you some technical background. So the first thing is, what is assembly? As most of you probably know, CPUs don't understand words or strings. They understand numeric opcodes. And assembly is basically the textual representation of these opcodes. So as you can see on this slide, we have an opcode 6A06, but the assembly representation is push 6, which basically means take the value 6 and push it onto the stack in memory. And we'll see a lot of assembly code in this talk, and also push instructions. The next thing I want to mention is registers. So we talked about CPUs, and registers are data storage units located on the CPU itself. And we can think of them as variables storing numbers. And in the code that we're going to see, registers are referred to by sequences of English letters like EAX, EBX, and ESI, and we're just going to think of them as variables in code. Now, when we talk about registers, there are two conventions that we must know in order to understand what the program does. So the first one is that in x86 architecture, the function return values are stored in EAX. So for example, we have a function that ends with the instruction move 5 into EAX, as you can see, and then return 4. But this function does not return the value 4. It returns 5, which is the last thing that is stored in EAX before the function returns. So this is one convention that we need to know. And the second one is that function parameters are pushed onto the stack before calling the function. So for example, we have here push the value 3 and then call myfunc. So we understand that myfunc receives one parameter. In this case, it's 3. And right after the function is called, it's going to access its parameters by reading them from the stack and use them and do whatever it needs with them. The last thing that I want to talk about as part of this overview is the tools that I'm going to use when hacking Minesweeper. So the first one is called IDA. Some of you may know it. It's a disassembler. What's a disassembler, you're asking? It's a program that receives another program as input and gives you all the machine code that this program sends to the CPU. So using IDA, we can statically analyze a program without running it at all. We load it into memory, but we do not run it. We just see the machine code that it contains. And the second tool that I'm going to use is called OllyDebug. It's a debugger. And this one actually does run the program in memory. So it lets us put breakpoints on the instructions and play the program, run the program until it hits certain breakpoints. And it lets us observe the system state at any given moment, the register values, the stack, the memory, everything. So now that we have the technical background, we can go into Minesweeper. And our goal this evening is going to be making Minesweeper start up every time, such that all the mines are marked with flags, just like you can see in the screenshot. I see some smiles in the audience. Some of you may have done that before, so nice. OK, so we have our goal, and now we're going to talk about the challenges that we're facing. So the two main challenges are as follows. The first one is that this program is complex, and I don't mean complex in the sense of it's hard to use or play. Every child can play Minesweeper. I played Minesweeper a lot. But even Minesweeper, which is a relatively small executable file, probably consists of many, many lines of codes and functions. And we don't want to read all the Minesweeper code. We have a very certain thing to do here. So we're going to have to find the code that is relevant to our mission. Now, the second thing is that as Minesweeper players, we're used to only interacting with the graphical user interface and seeing the graphical elements. But now that we want to change Minesweeper, we have to think how things are represented in memory. Now, knowing these challenges, we're going to build ourselves a solution strategy, which looks as follows. So first, we're going to find the code that initializes the mine field. Next, we're going to understand how a mine is represented and how a flag is represented in memory. And once we know that, we can change the assembly code so that we attach a flag to every mine. So the first thing we do is find the code that initializes the mine field. Now let's imagine being the Minesweeper developers. What's the most natural thing to use, given that the specifications are that Minesweeper starts up every time with a different layout of mines? So the most natural thing is probably using a random function. And I open IDA, and I go to the Imports tab that shows me all the functions that Minesweeper imports from other libraries. And what I see here is that it uses crand function, which is good. Now, another nice feature of IDA is that it lets me see what parts in the code use this function. It's called cross-reference. What places in the code reference this function? So I use this feature, and I see that the only place rand is used in Minesweeper is the following function, which is very small and sweet. And therefore, we're going to analyze it step by step. So what does this function do? First of all, IDA tells me that it has one argument, which it calls arg0. The first thing that the function does is calling rand. And rand returns a random integer between 0 and 2 to the 32. And it stores it, like every function, in EAX, the return value register. Now our random value is in EAX. And the next thing we do is execute CDQ, or convert double word to quad word. We take the 32-bit integer stored in EAX, and we expand it over two registers, EDX and EAX. And now it's a 64-bit integer. The next thing that happens is idiv, is a division operation. And we divide the number in EDX and EAX by arg0, our function parameter. Now what we do, the result of idiv is stored in two registers. EAX has the quotient of the division, and EDX has the remainder of the division. And so the next thing we do is move whatever is in EDX into EAX. We move the remainder of the division to EAX, and then we return from the function. So if we want to put all these CPU instructions into human-readable code, what this function does is basically calling rand and returning its modulo n, where n is the function parameter. It's a one-liner function, which I'm going to refer from now on as myRandomize. Now, at this point, I know where the function rand is used in Minesweeper, But now I want to figure out where this function, myRandomize, is used. So I use the cross-references feature again. And I see that myRandomize is used from this place in code. Now, just taking a broader look at this thing, this kind of looks like a loop construction. We have some code and then a green arrow taking us from the end of it to the beginning of the code block. Now we're going to go step by step over this code, which is just a little bit more complicated, but bear with me because it's doing cool stuff. So the first thing we do is push a value onto the stack, the value that is stored in 1005334, and then we call myRandomize. And the random number that's returned is an EAX, and we put it in ESI and increment it by 1. So ESI at this point holds a random number plus 1. The next thing that happens is pretty similar. We push once again some value onto the stack, and we call myRandomize again. And at this time, we increment the number by 1, but we also shift it left by 5, which is equivalent to multiplying the number by 2 to the 5th or multiplying it by 32. So at this point, we have two registers, ESI and ECX, each one holding a random number. And the next thing that happens is pretty interesting. We take these two registers and we sum them up. And we use this sum as an offset to a place in memory, to a location, 1005340. And we read the byte that's in there, that's in this location in memory, and we test it against the number 80. Now let's dig in this because it's interesting. 80 is a 1-byte number whose most significant bit is 1, as you can see on the upper row. And given a number n, when we test it against 80, what we actually do is a logical AND. And so if the most significant bit in n is 1, the result I'm going to get from this test operation is a non-zero result, is 80 in hex. And if the most significant bit in n is 0, then what I'm going to get is a 0. So there are actually two possible results for this test operation. Now let's get back to our code. So we read this byte in the random location in memory, and we see if the most significant bit is set in this byte. And now we have the jump non-zero instruction. So if the result is non-zero, we take the green arrow and we go back to the beginning of code. But if the result is 0, we go with the red arrow. And result is 0 means the bit is not set in our byte. And if it is not set, we do an OR operation between the byte in memory and 80. And this is equivalent to setting the most significant bit in our byte in memory to 1. Now, this might have been a little complicated, but let's review it in a more simple way. So what do we do here? We randomize two numbers, rand1 and rand2. And we sum them up, and we use this as an index to a location in memory. And we see if this certain byte in memory has a certain bit set, its most significant bit, if it's set or not. If it's already set, we just go back to the beginning and re-randomize two numbers. But if it's not set, we set it to 1. What is happening here? So if we think of this certain bit as a mine marker, this might be the actual code that initializes the mine field in memory, right? Because we randomize indexes, we check them in memory, we see, is there already a mine there? If there isn't, we put a mine there. If there is, we just re-randomize new indexes. Now, this is just a theory, okay? This is just a hypothesis. And I'm still not sure that I'm in the right place. And actually, there are some bits of information that are left unknown. So what are these parameters that are pushed onto the stack before the calls to myRandomize? And what is this base address in memory to which I add offsets? And this is where debugging comes to our rescue. So as I promised, Ollie debug, our debugger. I open Ollie debug and I see this. So the main, the bigger frame is the code, the assembly code that we just saw in IDA. As you can see, the highlighted push instruction is exactly the push instruction that we saw a minute before. And the smaller frame is the stack in memory. And the stack, as you might remember, holds the function parameters. So what I do is I put a breakpoint on the push instruction, and then I run Minesweeper until it hits this breakpoint. And what I see is that the value pushed onto the stack is 9. And I do the same trick again with the next push instruction, and again I see that the value is 9. So there's only one thing left for me to check, and it's this base address in memory, the array base, the base of the array. And I go to this memory region, and this is what I see. And I stare at this for hours, seriously. And finally, I recognize some repeating pattern here. And this is what I see. I see 9 repetition of a very similar pattern. And every repetition starts with a 10 in hex. And then there are 9 different values, and then again a 10. And I look at these values, and I see mostly 0f. But from time to time, I see also an 8f. And I count these 8f's in memory. And I see that there are exactly 10 of them. And then I recall playing Minesweeper as a child. And I remember that the default beginner board of Minesweeper is a 9-on-9 board with exactly 10 mines positioned on the board. And then this is how I look like. I go, oh my god, this is a minefield in memory. And I'm very happy. So let's sum up what we know up to this point. So when we see 10 in memory, this means that row starts or ends. It's a row delimiter. A 0f is a blank square, is a square without a mine. And 8f is a mined square, square with a mine. Now this connects pretty well with the code we saw before, because when we take a blank square, an empty square, a 0f, and we do OR with 80, we get exactly 8f. And now the last thing that's left to do is figure out what a flag is represented like, because we know all the rest. But this task is pretty easy at this point, because we know where the minefield is in the memory, and we can just run Minesweeper at the same time. So I run Minesweeper, and I choose a certain location in memory that has a mine on it. It's highlighted over there, as you can see. It's an 8f. And I right-click on the corresponding square in the Minesweeper board. And 1 second later, I see that the value in memory is changed into 8e instead of 8f. So at this point, I understand that 8e is a square that has a mine and is also marked with a flag. So the original operation was doing an OR with 0f and 80. And that gave us 8f, which is a mine. But now we want to create 8e. And there are a couple of ways to do that, but what I figured out was most convenient for me was just doing an XOR operation with 81. This is just bit algebra, bit arithmetic. And so there's just one thing left to do, and it's changing the executable itself. So I'm going to show you what I did in Ollie debug. This is the OR instruction that I want to use. It's the OR with 80. And I want to change it into XOR with 81. So I right-click on it, and I choose Assemble, which lets me assemble the code. And I change the OR instruction into XOR instruction with 81. And I assemble the code. And now what I do is save this new piece of code into a new executable. I don't want to override the old one. I'm just saving it into a new one. And I'm calling it patched. And I save it on my desktop. Now I open it, and all the mines in Minesweeper are marked with flags. And when I click on the smiley face, this behavior is preserved. Every time it starts up, all the mines are marked with flags. Thank you. So at this point, the mission is accomplished, and now it's your time for questions. Was it all clear? Yeah, sure. The calculator, of course. Anything else? OK. I don't see any more. Oh, sorry. Yes. I think IDA is able to disassemble ELFs, which is the Linux executable format. I'm not so sure because I have no experience with it. But there are definitely tools to disassemble and analyze Linux executables. And people do that. So I'm just into Windows. OK. Thank you very much for being here.